When I was little, nerd secrets were passed around in the locker room without anybody hearing, and one of the coolest nerd secrets I heard was you could take a pair of scissors and you could magnetize it if you only went like this. You had to go like this. And so I did this, and I did this like all the time, and I was like, hey, am I magnetizing the scissors? So I would get something else made of metal. Let's see, I found this thing here, and I'd say, oh, look at that, I magnetized the scissors. And then somebody said I could magnetize it the other way by going like this. Right? The other direction, and let's see if that works. Oh, it's still magnetized. What the heck? So how did I unmagnetize scissors? And that was what bothered me. And I was always thinking that I could go like this, just to confuse it. Which way are you going to magnetize? So all of these are just slightly untrue. But now that I'm bigger and I know more about magnetic fields, and I have a bigger pair of scissors, I can magnetize this pair of scissors with a magnetic field from a wire. Now that's much more agreeable, and we're going to be studying what happens if I magnetize this pair of scissors with a solenoid right here. Imagine lots of loops, but schematically we're just talking about a uniform-ish field inside this wire that I've wrapped around the metal. We'll talk about why that's a big deal and what happens as we magnetize it and then magnetize it the other way and such. So I want to think about these, and we're going to need 4 rules. These are the ideas or themes of the argument. 1 is that magnetic dipoles, remember we said that you can chop magnets down until you get to a fundamental dipole, and in the case of a ferrous metal, you're usually talking about a single atom that has one electron that's just not lined up with all the others, doesn't cancel out, and so you've got a dipole. Dipoles prefer, I'm going to say that I'm just going to use the gentle word prefer rather than always. I probably could use the word always. Dipoles prefer to line up. And by that I mean that if they line up with each other, they're all going to be lining up with each other. So just for the occasion, I wore this tie where all the penguins, you'll notice, are all facing the same direction. You could think of these penguins as dipoles. I know I do. And so these penguins are all pointing that way. I guess some of them are pointing that way. What I mean by their alignment is I mean they're all standing up that direction. Oh, here, like this, so that you can see them standing up like that. Anyway, in a particular domain, and we're going to define that in just a second, every single dipole is lined up with each other. It's like a region of a political boundary, and everybody in that political boundary is voting exactly the same way. So that's a domain. That's what defines a domain, where all of these dipoles are perfectly lined up. And why do they line up? I'm not going to tell you. It's quantum mechanics. But the point is that it is entirely perfect. Pretty much 100% of them are lined up the same direction in that domain. But remember, outside of the domain, and the domains are small, this pair of scissors right here could have thousands of domains for easily. But inside of each of these domains, there are billions of atoms that are lined up. In principle, we could think about a dipole as just being some iron atom that's pointing in a certain direction because of that one unbalanced electron. But outside of this domain, and there's a domain boundary right here, but outside of that domain, there's another domain. And rule number 2 talks about which direction that domain wants to be oriented. Now, there's something about lining up with the crystal structure, because inside a metal there are little tiny crystals that are pointing a direction or another direction, and they have a grain structure. And so, yeah, domains prefer to line up with or against that grain. It's not required, but they like to do that. But then there's this other effect that's kind of the opposite of point number 1. Point number 2 says that if a magnet is in an external field, it prefers to have its field line up with the external field. So I want to think about this domain and which way those little dipoles are going to be pointing. But to do that, I have to draw the field of this domain. And that field will be doing this. Don't you agree that field will be coming out of the north side and going into the south side? So it's coming out here, and then there's probably a field line over here, and probably another field line over here, maybe one here and here. But generally, we're getting a field that right next to it, oh look, right next to it, the field's not pointing to the right, the field's pointing to the left. And right underneath it, the field's pointing to the left also. So right next to this domain, we're very likely to have this brown domain have all the spins pointing the other direction. Those little quantum mechanical dipoles will be pointing to the left. So when I think about the thousands of domains that exist inside these scissors, I'm thinking in general those domains are going to be completely canceling each other out. Every individual domain is perfect, but the domains are all jumbled next to each other, and they prefer, based on rule number 2, to cancel out. And how should I write number 2? I should probably say something like magnets line up with B external. They line up with the direction of the external magnetic field. That's rule number 2. Let's go to rule number 3. Check it. Rule number 3 says that there's an energy associated with the magnetic torque. If something is not facing the right way, then there's some energy associated with it. And rule number 3 is not a big deal, but I'm going to say that the energy goes up if the domain is, let's see, if it's aligned is opposite. I'm going to say if it's opposite to the external field. And then I can give you the corollary. Energy goes down if domain parallel to the external field. Okay, fair enough? Fair enough. There's an equation for it. I can tell you the energy between two small dipoles, and that's, I guess we get mu naught over 4 pi. And it has some really fun vector math in it. There's a dot product between the two magnetic spins. This is supposed to be m1 dot m2. Then you have to subtract. This is a classic dipole-dipole interaction. You probably see these a lot if you continue on in physics. Dotted into the unit vector, and then m2 dotted into the unit vector. So that is the energy associated with any randomly oriented two dipoles, and you can see that it gets smaller as the dipoles get closer to each other. And remember, of course, with rule number 3, we have to remember that nature seeks to reduce energy. We want energy to go down because storing energy in places is annoying, and nature would prefer to just get rid of all the energy as quickly as can. Send it to some other system. All right, that probably has something to do with some law of thermodynamics. There's rule number 4, and rule number 4 says that these domain boundaries right here, although you might think it's a boundary based on a river or something, some political voting reason, like these guys are near the nuclear power plant and these guys can't smell it or something, I mean the poop factory. All right, 4. Domain boundaries can shift. So what happens is, rather than actually telling this enormous chunk to go that way, I'm actually going to grow the purple domain boundary. If I put an external field on this to the right, then the purple boundary, the purple domain will grow. And if I put a magnetic field onto the left, then the brown domain will grow. It will actually invade into this territory. It's pretty cool. You can etch crystals and find out where the domain boundaries are. You can actually see them under a microscope. So all this stuff has been studied in pretty heavy detail, but these 4 rules all together lead us to hysteresis. So now the picture is this. I want you to think of charging up a magnetic, well, let's say this is a piece of iron, right? It's just some kind of ferrous metal, and if I put it inside, this is actually a coil, you can't see, but it's got a lot of turns. Can you imagine how many turns are in there? If it's that thickness wire or smaller, it's probably even smaller. But this ferrous metal will magnetize when it's in here. And this is actually a clicking device. It's used to make that click. I'm just kidding. It's used for some other purpose. But what I'm doing is, generally, I'm putting a current through here. So I want you to think of taking this Energizer battery made in St. Louis, Missouri, and making a current go through here to make a magnetic field inside the scissors. So we're going to start out with a picture like this. So let's magnetize a bolt. Here's my bolt. And I want to show the current going through here. So here's my battery, and I'm going to go around and then back behind, and around and back behind. and round and back behind, and then once I get through there, I'm going to come back over here. So we're going to make a current go, and that current will be that direction. So by the right-hand rule, I find that I'm a priori magnetizing this hunk of metal to the left. So let's see what I've got there. When I have current this direction, then what I'm going to be doing is I'm going to be making a graph here. I'm going to be graphing what I get. I'm going to say resulting magnetic field, and I'm graphing that versus the magnetic field without the iron in the middle. So without that bolt right there, I would be magnetizing, no, this is not really looking for a vector. Well, I kind of am, well, yeah, I'm kind of looking for a vector. I'm going to have negatives, that's for sure. So initially, I'm arguing that this bolt, excuse me, is not magnetized. That means that when I have no external magnetic field on it, then, so you could call this B external, right? I'm probably going to be using that language. Then I don't get any resulting magnetic field at the beginning. But then if I turn on the current, then I'm getting more and more B without iron, so I'm going over to the right, and I'm actually aligning the domains. I'm forcing the domains in the right direction to grow and the domains in the wrong direction to shrink, and I'm going to get this pattern right here where the magnetic field increases, increases, and increases, and then as the domains the bad domains get smaller and smaller and smaller, and the good domains get bigger and bigger and bigger, I get diminishing returns until I finally get to this point right here, which is called you win. We have magnetized all the domains. Some people like to be formal and call it saturation. And that means, like, if you are trying to saturate some solution, then you'd have all the solute that you could possibly fit into it. So that means all the domains are lined up, and that's the biggest magnet you're ever going to get. But the interesting thing happens as I remove the field. I'm going to turn the current back down again. Let's say that we can adjust this voltage right here. As I adjust the voltage back there, you see the domains prefer to be where they are. So they're going to lose a little bit. Remember, we were starting from, let's call it point A, and going up here to saturation, which I'm going to name point B. And as I reduce the external field, I'm going to be going from B down here to this location. And I want to call this location C. And I want to point out that C means there's still a magnetic field resulting. See, there's still a resulting magnetic field, even though there's no external magnetic field. That means that this iron is still sort of magnetized. Now, not as much, and at this level right here, I could call this, let's name this sucker, this guy is going to be called B residual. And I'm being really sloppy calling everything B. There's this concept called H that you could talk about later, but I don't think we need to get into that detail right now. As I continue decrease, now I've got current going this direction. I'm trying to magnetize the domains so that there's a magnetic field to the right now. But as I continue lowering this, eventually I will get to the point where the field becomes zero in the iron. But that took some forcing. I actually have to be pushing it with an external field the other direction. So I'm going this way, going down this loop right here, and as I continue pushing more and more, I'm going to get ultimately all of the spins to line up over here. Again, the diminishing returns over there. But finally, you win. We've got a saturation point again. Yay, you win. And let's point that out that that's saturation, of course, for all the people watching at home. And then, see, what happens is, if I now again turn around this current and try to now, well, I'm going to decrease it back to zero again. But watch what happens as I get back to zero. I can't follow the same curve. Watch, because the domains are sticky. Again, the domains sort of want to be where they are, because there's energy associated with moving them. Oh, remember how I said you could actually unmagnetize these scissors? You could hit them. you're giving them some mechanical shaky energy that allows them to find their more natural orientation. And again, I want to tell you that their more natural orientation is one domain like this and the domain next to it like that, because that reduces the net magnetic field inside the material, and magnetic fields cost energy money, so you got to pay sometime. So watch what happens here. Right now I'm decreasing the current, which was going to the right here. Oh gosh, here I actually had the battery pointing this direction for this part of the adventure. And for this part of the adventure, I had the battery pointing that direction. Can you get that picture? At this point, the battery is off, but there was still a magnetic field. So here I've got the field, and the battery is going this direction, but it's decreasing as we're going that way, and here we were increasing as we're going that way. Okay, you got the idea? Now I'm going to be turning down my power supply, so the external field, the field without the iron in the middle, would be getting lower. So I'm walking down here, but I notice that I've still got some residual field, and making this symmetric is going to be really hard for me, but I'm kind of thinking it's going to be kind of like right there. Yeah, I've still got some residual field. Residual is right there, and let me point out that I have to actually push the other direction. Here I have to push the other direction to get the field in the metal finally to go to 0, and I can get back up to here. And then I can do the whole cycle over again, but notice that it has to do with the history of where the magnet has been. And you're thinking, wait a second, did he just say that hysteresis has to do with the history of the magnet? Hysteresis. Fun fact, it's a Greek word, but it has nothing to do with history. It in fact has nothing to do with hysteria either. It has everything to do with lagging behind. So the magnetic field that we get, the resulting magnetic field, is lagging behind the field that we're trying to make until we get to these two saturation points. And based on this model, where we're making a magnetic field right or left with this, we can never get back to that center point right there, because I guess you'd have to hit it in the absence of a field to get all the domains to randomize again. The domains randomize right there. I guess if I go to right here and then decrease back to 0, then that would work. But this loop is really beautiful, and there's something about this height right here, the height in the middle, the residual field. If you have a material that has a very strong residual magnetic field, you might want to use it, for instance, to make credit cards, right? And well, I can think of some things you wouldn't want to use it for, but if you want something to hold its magnetic field for a long time, then you'll probably use that material to make credit cards, because you want your credit card to have the same magnetic field for years, and people are going to be swiping it through stuff and such. Okay, so I wanted to show you one example of how this hysteresis loop works. No, just kidding. I don't want to look at how the hysteresis loop works. What I want to do is I want to show you that making a resulting magnetic field, this is huge. The resulting magnetic field is freaking enormous compared to a very small external field. And this is the message. The message is, if you want to take over England, you don't go in and invade England. You convince the domains inside of England that they like you, and then England will take over itself. So what we're doing here is we're having this bolt take over itself. The magnetic field that results from just taking these domains and convincing them to align up with my field is absolutely enormous. I'm talking about thousands of times bigger than the field that I can actually make just by my own brute force of the current. So let's do a really quick example of that. There's all kinds of magnetic stuff underneath this table, which is kind of frustrating. So here's what I'm going to do. I want you to watch that compass right there. All right, there's our compass, and I'm pointing this so that if I make a current go through, then I'm going to turn it. Right, watch that. You see that turn a little bit? It turns just a little bit. That's the current that we're going to get through there, and that's the magnetic field that we get as a result. I guess if it turned 90, then we'd have an overwhelming field from this guy compared to the other one. So I'm going to put this iron bolt in here, and the iron bolt is magnetized a little bit already too, so I have to turn it a little bit to get back to nothing. Just notice how much it turns now that the iron bolt's in there. Look at that. Holy cow. I'm talking about thousands of times stronger field now that the iron bolt's in. Look at that, wow. And that's because all I have to do is convince these domains that they want to fight for me. And oh, by the way, this is a very soft magnetic material, so the residual magnetization is very small because as I do that, then it's gone after I remove the current. It's completely gone. So in that case, we would have a hysteresis loop that's very, very small. But a hard magnetic material has a much taller hysteresis loop, and that lets you distinguish between hard and soft magnetic materials based on their residual magnetic fields. Of course, saturation point is different for every type of material as well, but if you're designing something like a transformer or something like this, maybe it was used as a relay originally, you probably want a soft magnetic material so that you can make this make it go into the machine and then back out of the machine. Maybe there was a spring that was holding it right here, and we could turn on and off some valve on maybe it was a solenoid for a car or a washing machine. Who knows? Good luck.